Hey students, welcome back. We're still in our solutions unit, but we're going to switch to a topic that is probably completely new to you because it's one that really just works best in AP chemistry. By this time you have enough foundational understanding of other parts of chemistry to really understand this. They love this topic on the AP test, so certainly I would be remiss if I didn't cover it. And we are going to cover spectroscopy theory and some generalities. And then you're going to be doing a virtual lab over it. If you're in the classroom, I'd actually have you doing a real life lab over it. But just letting you know, it's going to be virtual this time. I'll discuss more of that in class. But you're gonna want to make some notes about spectroscopy. This works for most general kinds of spectroscopy like they would ask about on the test. And I try to hit the things that I see them ask most often. So here we go. Spectroscopy is a way to determine structure and concentration in a mixture of a chemical species, okay? So you have a mixture, more than one thing put together. We can figure out structure or concentration of those things using spectroscopy. How does it do that? Well, I'm glad you asked. So I want to introduce you to the electromagnetic spectrum. And I hope that this is just a reunion, that you have seen this last year in pre-AP chemistry. If you're taking physics, maybe you've even seen it in physics. This is the electromagnetic spectrum. All electromagnetic waves are kind of shown here. So everything from AM all the way through gamma rays. And you can see visible light. The part we can actually detect with the molecules in the back of our eye is a small, small portion of that. Now, speaking of, it really is a lot like the molecules in the back of our eyes are a type of spectrometer in the way that it works. The incoming light activates some bonds and twists some things. And so as you're going to see, that acts kind of like a sort of a form of spectroscopy, okay? But anyway, parts of this electromagnetic spectrum can affect molecules in various ways. In the microwave region, that is enough energy to get molecules to rotate, okay? Now, that's exactly how a microwave oven works. I know you probably don't even call it a microwave oven anymore, right? That's exactly how a microwave works. It rotates the water molecules in the food, and literally then the friction of them rotating around increases the heat of the food, and there you go. The more water in the food, the better the results in the microwave are going to be. If we get higher in energy, so how do I know I'm going higher in energy? Well, okay, so here's how it works. Just a reminder, and we're actually going to come back to this later. Look at the length of the waves here. Okay, look, notice how they start really long and then get really, really tiny. Okay, wavelength is inversely proportional to the frequency. So down here are the frequencies. How many waves pass per second? Notice with long waves, we have a frequency here. And with short waves, we have a frequency here. So much higher energy, or sorry, frequency here. A 10 with 18 zeros after it. Lots of frequency. With short waves, small waves, we get large frequency, and frequency and energy are directly related. So high amounts of energy. So on the left, low energy, on the right, high energy, which is good. I don't expect to have issues with AM radio waves, television stations, FM rays hitting me all the time. They're shot out into the air all over the place, especially where I live in the Metroplex. It's a ton of radio signals hitting my body every second, and I don't worry about it because it's relatively low in energy, not going to damage me. A little higher in energy microwave, yeah, now I'm probably going to be a little worried, okay? Please don't stick anything in the microwave that's not meant to go in the microwave. Higher in energy than that, we get infrared. Now, our skin actually has heat sensors that can detect the infrared radiation. I still can't see any of this. It's all invisible, but I can detect it. It will feel hot. And when you sit at a fire and most of the convective heat of the fire goes straight up because that's, you know, how heat rises, right? But still, the side of you facing the fire just feels a lot of heat. That's that infrared radiation waves hitting you from the fire directly. And that's also why the backside of me gets really cold, because it doesn't have any of that infrared radiation hitting it. It's just my front side. Higher in energy than that, we get UV vis, okay? And so ultraviolet and visible light. And this is high enough we can move electrons. So we go from kind of low energy where we can only spin molecules. I mean, just think about like a toddler can kind of knock over a toy. Okay, that's the same way, low energy with microwaves. Little higher in energy, infrared can vibrate the molecules. Now the bonds, if I haven't said this in class yet, they really are a lot like a spring. The best way to model the bonds in a molecule, you know, with something you can touch, would be with springs. And so they can be pulled apart, they can spring back together, back and forth, okay? They operate like springs. So what's it take? I know there's this exercise equipment, you like grab it and you like work on your muscles by pulling apart the springs. Well, that takes a lot more energy than just taking that and, you know, knocking it over. So it takes more energy to get them to vibrate, to stretch and contract and things like that. And then it takes even more energy to get the individual electrons to move higher in energy levels. And that's what that ultraviolet and visible light region can do for us. Do you remember seeing this? Okay, so when the electrons absorb the energy in that ultraviolet visible region, they move to a higher energy level. We call that absorption. There you go. We can measure it, okay? In fact, that's what Mr. Bohr did to find his Bohr model. Too bad he didn't know of the ultraviolet region here and the infrared region he couldn't see. So if we use machines to detect all that radiation, we can get the full 7 energy levels that the electrons can have in atoms, and we have 7 energy levels on the periodic table. That's how it all works out so far, right? Okay, well, they won't stay there. Eventually, they will release that energy and they'll fall back to their ground state, and usually the release is visible light. So we can measure how much they absorb or measure how much they shoot off. In a previous unit, we looked at what they shut off, and like here's neon, and we saw that its electrons could release light as these bright lines here, making a fingerprint or barcode, some students were saying, for an individual element. That's very true, right? Okay, what we're going to look at today is not measuring them releasing it, but measuring them absorbing it. We're going to measure the absorption of light as it passes through a collection of molecules. Okay, that is due to the Beer-Lambert law. Actually, Mr. I can never say his name well, Bohr, first came up kind of with this idea, and then Lambert expanded upon it, and then Beer finally put it together into an actual equation that you see before you. We'll get to that in a minute. But thanks to all the work of these chemists, we can use spectroscopy. That is a measurement of the light that's absorbed to determine the concentration of some unknown colored molecule. And we only need to be given a few pieces of information. Now let me pause here for a moment. When we can't use spectroscopy is when the molecule does not absorb in the region of the electromagnetic spectrum that our signal is. Typically in class, we're going to be using visible light your eyes could see, or ultraviolet, often called UV vis for short, okay? If the electrons absorb, as I showed earlier, if the electrons absorb in the infrared region, I could not use UV vis spectroscopy. I would need a machine that could measure infrared spectroscopy to do it then. And I'd have to go with what the machine tells me. I mean, we're kind of going through what the machine tells us anyway. So be aware, for UV vis to work, for especially visible light to work, we need colored molecules. It would not be appropriate to use spectroscopy for colorless, clear colorless liquids. Even if it's a mixture of them, it would not be appropriate to use that. I would need to use something else. Maybe ultraviolet could work, maybe infrared could work. We would need something else. Visible spectroscopy only works if they are colored molecules. Now, the formula that Beer and Lambert and everyone finally got to is this one, and it looks kind of weird. Think of it as A equals ABC, okay? We use a fancy looking E here to stand for absorptivity constant, which is why I like to call it A for absorptivity. But that's the molar absorptivity constant. So A is the absorption, and we're going to call it, and some people call absorbance and like synonyms, okay? No big deal. So the absorbance or the absorption is equal to three things. A molar absorptivity constant, and just like the name sounds, it is constant for a molecule. So every time I use, say, sucrose, I know I can look up its molar absorptivity constant and know what that number is every time I'm dealing with sucrose. It's constant for sucrose. Now, if I'm using glucose, I can't use that number anymore. I need a new number, okay? B stands for the path length, and we just chose B, so it could literally go like A, B, C, okay? And then C for concentration. And yeah, you guessed it, that concentration is going to be in molarity. Guess why we already discussed molarity and dilutions, because we're going to be using them for all this, okay? So this is our formula. Now here, now note this, okay? If we always test the same colored molecule, say I'm testing blue 1, okay? So blue 1, brilliant blue. I'm using the same blue for my entire lab, then that absorptivity constant is a constant. It's the same. And if I use the same size cuvettes each time, and we'll get to that in a minute, the path length will be the same every time. So it's also constant. So if we get rid of those two, we can see really what we can see. I'm going to even scribble them out. I want you to see this. If this is a constant, I don't need to worry about it changing. It's not a variable. If this is a constant, don't need to worry about it changing. It's a variable. Look at what I got. I got a nice, simple, direct relationship between absorbance or absorption and the concentration. What's this tell me? The higher the concentration of the molecules, the more they will absorb. Well, okay, that just makes sense. But this would be like why there's red food color in strawberry Kool-Aid, and there's red food color in pink lemonade Kool-Aid. Yet one looks red, one looks pink. The concentration in the pink lemonade is less, so it absorbs less light, okay? And so it looks less red. And the concentration of the red in the strawberry Kool-Aid is greater, so it absorbs more and it looks like a darker red. So very handy little trick we do as chemists to make both of those constant, and therefore we have a very nice direct relationship between. In fact, we'll even have a number. We'll combine those two into one number. I don't know, I'm going to throw a number out there, 237, okay? And we'll be able to compare very much on a nice, easy equation, those right there. Boom, done, kind of a thing. Okay, so that's how the equation works. You don't need to memorize the equation for the AP exam, but it is on the formula chart, so it's something to be aware of. What you really need to be aware of is in spectroscopy, the greater the concentration, the greater the absorption, or the more it absorbed, the more I can infer it was concentrated. That's what they're going to care about. Okay, so how do we do spectroscopy? Well, shocking. We do spectroscopy with a spectrophotometer. I know, don't you love these big fancy words? So you can be, so when your parents ask you, hey, what'd you learn today? You can talk about, well, we use spectrophotometers to figure out the concentration of a colored molecule using spectroscopy. And they will probably just stop the conversation right there, won't they? It'll be lots of fun. Okay. Anyway, so a spectrophotometer is a device. They're more and more now, they're digital, like the one you see before you. I'm kind of surprised it doesn't have like a lid to it. Maybe it's just been removed to show the parts of the spectrophotometer. But here's the basics. You need a device that can send wavelengths of a known size, because size is color, wavelengths of a certain size through a sample and measure how much it's absorbed as it goes through, okay? Measure how much is missing. So maybe no, it's sending in, I'm just gonna throw out a number, 8. but it only receives on the other side 5. Then absorption is 3, kind of an idea. Now, that's not the numbers you're going to be seeing, but that's what it basically does. We could also measure transmittance. In AP chemistry, we really don't measure transmittance. We measure absorption. Just go with that. So here's the inner workings. We have some sort of light source, and it's put through a slit that makes it a single beam and not just a spread out thing, because that would not be easily detected. Then when there's some sort of color filter, usually you can, in the old fashioned, you could literally dial to get a color. Now you set it to a wavelength, and I'm sure inside it moves some sort of filter to make it work, okay? That colored light goes through a sample, and how much it gets absorbed is detected by the detector, and it just comes out on the little readout right there. So these are awesome now. The new ones, I love, especially the ones they can hook to a computer and have Excel do the work for you later. Love that. That's hopefully what we're going to do in class if I had you in class. Virtually, you're going to be able to do the same thing. Get your information, and if you want, you can put it in an Excel and let Excel do the work for you. But I'm getting ahead of myself. Let's keep going. So what do we need to do? You have to do spectroscopy. Well, we need a spectrophotometer, and then we need a solution of a known concentration. So that's what I've got here. See my purple known solution made in my volumetric flask? Oh yeah, we talked about how to make this, right? So how do we make a known solution? You measure out the grams, you calculate the grams, you measure out the grams, you pour it in with some water, you fill about half full, you swirl it, you fill it most of the way, you stopper and invert it, and you go drop by drop until the meniscus hits the bottom, that little mark on the neck, okay, right there. You get eye level, make sure the meniscus hits it, go drop by drop, and then you got exactly a well-made solution that you know the concentration of, right? So we need a concentration in a solution that you know. We need a known or a standard. And then you need an unknown. In this case, since my known was purple, I was like, hey, let's grab some purple Kool-Aid. So what we could do is literally find how concentrated is the purple in that Kool-Aid. That's what we would find. Now, I am pretending that this purple and this purple are one molecule and the same. I'm pretty sure in Kool-Aid it's a red molecule and a blue molecule. Let's not get into that, okay? We'll discuss molecule differences in a minute. Okay. So you have a known or a standard, and then you have your unknown. Let's put the unknown to the side for a minute. You're going to take your known and you're going to make lots of different concentrations out of it, and usually a blank too. So this known it's Kool-Aid, right? So this known was made with water. So there's my blank of pure water, no colored compound at all. And then I took some of this to make, diluted a little, and some of this diluted it more and diluted it more and more and more and more. So I get a nice set of different concentrations. Now, how am I going to know these concentrations as I dilute them? Right. M1V1 equals M2V2. You're going to do it each time. You need to know the new molarity once you've diluted it in these. So I had the original molarity, M1. You take out some volume, V1. You fill it to the line, V2, and you know your new molarity. Okay? So that's, again, why we did that. Now, I want to harp on this a moment. The blank here, because it's Kool-Aid I'm going to be testing in a minute, I'm going to use just water for that. I have a spectroscopy lab for equilibrium where you use iron, but we need to keep iron in a particular oxidation state, and in order to do that, I need to acidify the solution and put in a few other chemicals. That solution without the iron looks yellow. The iron I want to detect, when the iron's placed in it, it turns blood red, because iron's in the middle of hemoglobin, and that's why your blood is red, the iron in it, okay? So it turns red or reddish orange sometimes with the iron in it, but without any iron at all, it's still yellow. My blank would be that colored yellow solution of everything except the iron. That's what I'd want as my blank, okay? So your blank is what you're dissolving, the thing you're looking for in. It should match everything except for the colored species, the colored molecule. So I take each of those. Let me go back a slide. I don't know how easily I can go back a slide. Oh, yay, that worked. I take each one of these new solutions that I still know the molarity for, and I put them in a cuvette. So here's my little great big cool cuvettes. There's my blank there. So here's a really, really dark one, not so dark, not so, you know, you get the idea. Okay. I take those and I put them in the spectrophotometer. Now notice, all of these cuvettes, that's the name for them, all these cuvettes are the same size. That's awesome. Keeps the path length the same. And if the path length is the same, then absorption is directly proportional to the concentration. And that's exactly what I want to exploit to make this lab work, okay? We're going to take them and we're going to put them in the spectrophotometer. But before I make any measurements, I want to know what is the best color to use. Now, if I'm looking at purple, I can tell you I don't want to use purple because that's what's being transmitted to my eye. I want to do what's absorbed. Best thing to do, and you're going to have to always do this, take your darkest solution, put it in, and just cycle through all the color choices until you find the one that absorbs the greatest. Why do you want the greatest absorption? It will minimize errors. If with this dark one I pick the most absorption and I have some error in the mixing in between, it's not likely to damage my data too much. If I picked something that just barely absorbed here, and then I messed up one of these, suddenly I'm going to get a huge outlier thing, like I'm going to have a number that does not fit well with any of the others, okay? It minimizes the error to pick the greatest absorption, and that changes with every color. If I do purple Kool-Aid in station 1 and I go to station 2 and do red Kool-Aid, I'm going to need a brand new wavelength for the best absorption. If I then do a blue Kool-Aid in the next station, I'm going to need a brand new wavelength for the best absorption. Okay? I can guarantee you if you change colors, you'll need a new wavelength. I can guarantee that much. What wavelength is it? I don't know. You have to test it. That's the first thing you do once you've all set up all your cuvettes. You find that greatest wavelength. Now, you be very, very, very careful as you manipulate your cuvettes. You don't want any fingerprints left on the sides or anything else for that matter, no drips or anything like that, okay? So you take your cuvette, and often, especially in college, by the spectrophotometers, will be a box of very special wipes that you can wipe the cuvette with and be certain that you are not leaving fingerprints on it and wipe away grease or anything else, okay? These square cuvettes, I love them. Two sides have ridges for you to grip onto, and then two sides are totally smooth for the light to go through. And as long as you grip the ridge side, you know you will never leave fingerprints on the side where the light's going to go through. And that's how we get around that. But still not a bad idea to wipe them, okay? Obviously, the cuvette should be extremely well cleaned out with, you know, water, deionized water, and then rinsed with your blank before you use them, okay? Because you don't want to take your time to mix up all these other molarity solutions, pour it into a cuvette that still had a few drops of water in it and have it dilute to a different value than you knew. If you mix it with your blank, it's not as bad, okay? Even better, rinse it with some of the same solution you're about to pour in. I mean, we mix up a lot, and you only need a little in the cuvettes. You can pour it in, dump it out, pour it in, dump it out, rinse it well that way, and then pour it in for a good sample. Even better. Okay. So all that setup's done, and really, like, that takes a long time. Half the lab, I would say, most of the lab actually is setting up to do all this. Once you have them set up, you just pop them through your spectrophotometer and you make up a little chart like this. Now notice the chart I've got. So here's my concentrations and molarity. My blank has 0. My little individual mixtures, I should see, you know, a change in the molarity. Now I know what that molarity is because I calculated that every time I did my particular dilutions. So I just write that in. Now often we actually measure this in millimolars, okay? A millimolarity. Milli as in 1,000th. So this would be 1 millimolar, this would be 2 millimolars, 3 millimolars, 4 millimolars. Same thing, just keeps us from having a decimal in a weird place. I don't mind decimal numbers like this, so I just leave them like that. You could use scientific notation, that would be great. You could put it in millimolars and work it that way, and that's fine too. Now be careful. If up here you say molarity, but then down here you use millimolars, now you're wrong. Or if up here you say millimolars, and down here you use molarity, now you're wrong. Make sure the label and the numbers match. Now, how do I get the absorption or absorbance side? From the machine. I love the digital machines that just tells us. It tells us the number like, 0, 0.21, 0.41, 0.65, 0.85, whatever. Here, my very last one, I didn't include because you get the idea, 1.02. So there we go. You just get the number. That's all you need. All that setup is for getting those numbers. It seems really crazy, but it's worth it. All right. What do we do once we have our chart? We graph it. Oh, look at that. That's a pretty nice graph. So I did this in Excel, made it nice and pretty. My title, absorption versus concentration. Here's my absorption. Here's my concentration and molarity. Had Excel, spread my numbers well. My blank is a 0, 0, so I know my y-intercept is 0, 0. Okay, it doesn't have to be 0, 0 for your y-intercept, so just be careful, look at your data. And then it plotted my numbers, and I had Excel do my linear regression for me. If you're doing this by hand, you do the same setup, title, 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 numbers, numbers, draw your big dots, and then you take a ruler and you start at 0, 0, if that's appropriate, and you draw one straight line that tries to go through as many as possible. Now notice my line kind of missed that one and kind of missed that one. That's okay. It's a best fit line, and best fit lines are an average of the data, and we'd much rather work with averages of data than try to work with each individual data point on its own, because that could get crazy, especially if one of these, I've had many times students doing this in lab, and for like this one here, instead of 0.65, they got like 1.25. And I look at their data going, there is no way that fit your data, do it again. And so they rinse everything out and they do it all over again, and then they get something closer to 0.65, and I'm like, see, that was worth it, okay? That's why we like an average. If we have that average, we can figure out if something did not go well. What we do then is we measure our unknown. So I put my unknown in the spectrophotometer, and notice I've added a line to my chart here. The machine tells me my unknown concentration, my grape Kool-Aid in this case, is 0.57. I don't know what the concentration is. That's what I'm trying to find. That's the entire goal of the lab. What is the concentration of the purple in my grape Kool-Aid? If the machine tells me it's 0.57, what can I do? Well, one thing I can do is I can go, okay, 0.57 is about here. Let's draw it over, which down here, maybe that's 0.0026, maybe that's 0.0027, something in there. I have a pretty good idea what the concentration is now. Yay, I've won. I beat the lab. Well, does that really seem great to you to say it's maybe 0.0026 or 0.0027? Yeah, not so great. There is another method. We find the slope of the line. And very nicely, since the y-intercept is 0, that part falls off. And then I calculate it. So if my absorption y, catch it, if my y is 0.57 and I solve for x, I get numerically, oh, my calculation tells me it is 0.0027 molarity. So up here where I was kind of guesstimating, down here I know for a fact with that slope of the line equation. Now I had Excel do this, and that's why I love these devices when they're hooked up to Excel or some other graphing program that can do that for you. If you're doing it by hand, you have to do your good old rise over run calculation. It's that easy. You find your slope, no big deal. Okay, be sure you're looking at the average line though, and not any one particular data point when you find that rise over run. I would find something convenient. Is there anything convenient? This one right here looks pretty good because it looks like it goes right through the crosshairs of the graph. You might check it like there and then somewhere up over here, okay? Right here looks like it goes through the middle, so it'd be right in between 0.0035, 0.004. You get the idea. But you get the slope of the line, and then you know the y value, the absorption, and you solve for X, the concentration. And there we go. There, I've won the lab. That's what the whole goal of the lab was, to find that number. So the purple concentration in my grape Kool-Aid is 0.0027 molarity. There we go. That's what I can do. Now, this is in class we do water and Kool-Aid because it's safe. In chemistry, you would do chemicals that you really don't know how much they are, and maybe they're dangerous. We could do this if it's a colored pollutant in our water. We could do this to measure the concentration in our drinking water, sort of a thing. Okay, very important, but also something I don't want to, possibly mess up. And that's why I like using like Kool-Aid or lemonade or something like that in class. Okay, final thought for you. What if the thing you're testing is darker than your original standard solution? Believe it or not, you should know an answer to this already. But again, this is my original solution before I did any more diluting of it to make the little samples to chart. This looks way darker than that. What do I do? Well, let's go back to the graph. Say I don't do anything with it and I put it in the spectrophotometer and I get an absorption of 1.68. I'm like, oh, that's nowhere on my graph. Do not ever do that thing I saw middle schoolers do where you start drawing the lines off the provided graph paper going up this way and you draw them off this way and you do find where 1.68 is and put a new dot and see where the line goes. No. That's bad chemistry. Bad chemistry because we're not so sure of these numbers in and of themselves. What happens when I extrapolate that line way out there and I'm even having to draw it by hand now to fill it in? Huge amounts of error. We don't do that. So if we can't do it graphically, how do we do it? Mathematically. Exactly. You know how to do this. You can handle this. I just need this to be not so dark. I need it to be more dilute. Exactly. I very carefully take my really super dark compound and I dilute it until it would fit somewhere in the graph that I've already made. M1V1 equals M2V2. You know how to do that, okay? So you would dilute it until it fits. Now, therein lies the other thing. You're adding an extra step at the end as well. So a new step at the beginning to get your unknown to fit in your data, so we minimize the errors, but a new step at the end. And let me illustrate it this way, and I'm sure it'll make a lot of sense. Let's say I have to dilute this dark grape 4 times to get it to fit. It's now 1/4 the concentration, okay? When I get my absorption and I measure the concentration, that's not the concentration in the original plastic bottle. That's the concentration I diluted by 4. So to get the concentration in the bottle, one final step, I would multiply that concentration by 4. So whatever I did to dilute it in the first place, I would literally have to remember to undo that at the very end to get the original concentration. It really is M1V1 equals M2V2 all over again, okay? But that's what we do. So you could really make it easy on yourself. Take 1 part this, 3 parts water, and see if a 1/4 concentration works. And if it fits, then you just know your final answer, you're going to multiply by 4. If 1/4 doesn't work, maybe 1/5 would, maybe 1/6 would. There's no magic number for anything. You just very carefully, with good measurements, dilute it until you get to where it fits. You could go 1/10. And then your final answer for the concentration in the original bottle, you multiply by 10. Okay? But those are important steps. If you need to make it fit, don't forget to do that final multiplication to get back to the original in the container. Okay? It really could end up being an M1V1 equals M2V2 situation. So if you want a formula for it, it would work. All right, so that's spectroscopy really in a nutshell. But like I said, this is just the setup so that you can now go do a virtual lab of spectroscopy. If you were in my classroom, we would do an actual lab of spectroscopy. You now understand how it's going to work. And there we go. So I wish you luck in the lab. It is something you're going to be submitting. You're actually going to write up a full formal lab report for it. I'm going to give you some more details. And you're going to be submitting that for a grade. And the good news is, if you do it well, I always get great results on spectroscopy lab. Okay, so you'll get great results. But even then, your results are a small fraction of your grade. It's all of the thought you put into it to get there that counts for most of your grade. So do the lab report well. Good luck on your lab. I will catch you next time.